application of classical mechanics, and also underlying the associated hybrid equations that we developed. So they were presented in earlier talks, right, by Cesare and Denis. So I will mainly concentrate on the underlying geometric structure. So for instance, I will present the relevant unitary actions, the momentum maps, how they help understanding the quantities that appear related to these equations, such as, for instance, the link with the Liouville equation or the Madelung formulation. There is also, as you will see, an interesting link with geometric quantization that I will try to explain. And if time permits, I will also explain how one can use this geometric structure to treat a larger class of classical quantum systems, such as spins, and propose an equation for this that we can later discuss. And we are really happy to, looking forward to have your suggestions about what we propose. So let me start with showing you if I can flip, yeah, the plan. So I start with the Koopman-van Hove formulations that you have seen, but I will concentrate on geometric aspects. Then I will move on to the classical quantum hybrids that were discussed. Here also, I will concentrate on symplectic properties, unitary actions, etc. Then I will, in third and fourth, I will show how can one use this to propose, for instance, equations for classical quantum spin systems. So let me first start with some fundamental notations that I will use during this talk. So first, about classical mechanics. So concerning the classical mechanic approach, I consider a configuration manifold Q, and I assume the systems move on the phase space T star Q and given by some Hamiltonian functions. And the important canonical structure on the phase space are the canonical one form denoted by A and the canonical symplectic form. So these are the objects that will underlie all our constructions. On the classical Hilbert space of wave function, this space of L2 functions on T star Q, we consider the ordinary Hermitian inner product. And also, we will also need to use this pairing and the symplectic form here, omega. So all this is standard. It's just here formulated for phase space wave functions. So here I'm writing the KVH equations that you have seen earlier, which has two terms, right? A Poisson bracket term between the Hamiltonian and the wave functions, and this Lagrangian term that you can see here, this LH is the phase space Lagrangian multiplying the classical wave function. So here it's the connection, it's the canonical one form applied to XH, which is the Hamiltonian vector field. And so this is just P times dH dP, right, in coordinates. So you have really the Lagrangian on phase space. Here, these are the standard notations that I use for the Hamiltonian vector field. Here, the Poisson brackets in intrinsic form, and the Lagrangian that I have mentioned. So this is just to recall you the form of this KVH Liouvillean that we use. And remember from the earlier talk that this is the ordinary KVN Liouvillean modified by this Lagrangian. So interestingly, this self-adjoint operator also appears as the pre-quantum operator in the process of geometric quantization. I will explain much more about this later. Now it's just an observation. So I recall this KVH equation is for classical mechanics. It's Hamiltonian systems with respect to this Hamiltonian and this symplectic form. Now the goal of this talk I already mentioned, right, is to explore the geometry underlying this. Also, I will make link with pre-quantization with the automorphism and quantumorphism groups of complex line bundle that you will see. Then once we have understood what happens for the KVH equations for classical mechanics, I will explore the hybrid version of this and try to see in this theory the same structure and see how they generalize, how they adapt, what works and what has to be adapted. So very important concept in my talk will be the concept of momentum map. So this was introduced by Souriau and Constant in the 60s. And so I just recall the definition here very briefly. So if you have a Poisson manifold, right, with some Hamiltonian H, you can define the Hamiltonian vector field, right, which is this vector field such that the derivative of any function along this is the Poisson bracket of this function and the Hamiltonian. In addition to this, you also need a group action acting on P, on the phase space of the classical mechanical systems. And you assume that this action preserves the Poisson bracket. From this action, you can form the infinitesimal generator, right, which is just the derivative of the action with respect to the group at the identity. And the momentum map is a map from the phase space to the dual Lie algebra satisfying this relation. So let me explain this in more details. So this relation means that the Hamiltonian vector field associated to this map, when it is paired with some Lie algebra element, which I denote JXC, right? So this Hamiltonian vector field has to be equal to the infinitesimal generator of the action, right? The psi P here. So if this is satisfied, we say that we have a momentum map and we get a map from P to G star. So this map is crucial in classical mechanical systems, right? It's mainly useful as a conserved quantities from Noether theorem, right? It's well known if you have a G invariant Hamiltonian system, then the momentum map, if it exists, is preserved. It's also very useful if you want to reduce the dynamics on smaller phase space if you have some symmetry, which is known as symplectic reduction, as introduced by Marsden and Weinstein. But in this talk, we will see another very useful properties of momentum maps. So that's I would say this slide is the fundamental slide that help you, that will guide us through the rest of the talk. So momentum maps as Poisson maps. So remember that these momentum maps are from phase space to G star. So we can ask if they are equivariant with respect to action of G, right? So denoted like this. So on P, G acts using its own action, and on G star, it acts using the coadjoint action, right? Which is the natural action of the Lie group on the dual Lie algebra. So if this momentum map is equivariant, then it is a Poisson map. So it preserves the Poisson bracket from here to there. And here, there is a canonical Poisson bracket. On the phase space, there is the Poisson bracket of the system. On G star, there is a canonical, maybe canonical is not a good word. There is a obvious Poisson bracket, a natural Poisson bracket, which is the Lie-Poisson bracket, which has this form. So Fg, the Poisson bracket of these two functions at some moment mu in G star, is given by this formula. It's the pairing of the momentum mu with the Lie bracket of the derivative of the function. So the main tool that I will use throughout this talk is the following. If you have a classical Hamiltonian system on P, for instance, given by some Hamiltonian H, and if you can factorize these Hamiltonian through the momentum map, that is, if this Hamiltonian is some other H evaluated on the value of J, right, like this, then this momentum map sends the Hamiltonian system on P to the Hamiltonian system on G star. So this will occur many, many times in this talk, right, for some very important unitary actions. So more explicitly, if you have Hamilton's equations on P here, then applying J, you get the Hamilton's equation on G star with respect to this Lie-Poisson bracket. And these Hamilton's equations are the Lie-Poisson equations. So there are standard books that explain this very well. So these are two baby examples of momentum map. The first one, which I don't explain, is the case of a canonical phase space with a natural action. But the one that we'll use is the case of a linear action of a Lie group on a symplectic space. In this case, such action always have momentum map given by this formula. So J of V paired with Xi in the Lie algebra, because I want something in the dual here, is given by this quantity. 1/2 the symplectic form evaluated on the infinitesimal generator paired with another time the vector V in the space. So let's keep in mind this formula, which will give us many important objects in what I will present. So momentum maps are everywhere in classical mechanics, right? Without going through the details, I just wrote down 3 examples here as a Lagrangian to Eulerian maps in Lie group invariant systems on Lie group, like rigid body mechanics or ideal fluids. Also appears as a fluid natural maps from plasma equations to barotropic fluid equations, appearing here in the form of taking the moments, or also as Clebsch variables for ideal fluids. Clebsch variables, which were the first attempt to understand fluid mechanics as a Hamiltonian system. So they can be also explained by momentum maps. So that's not what we will use. That's not these systems that we will consider, but really this KVH approach in quantum and hybrid classical quantum mechanics. So the first action and the first unitary action that interests us is in the context of this KVH equation. So there are, as you will see, there are 2 main unitary actions that play a role in this classical theory. The first is the unitary action of the automorphism group of these principal bundle over the phase space. So T star Q is the phase space of my mechanical systems. S1 is the sphere. I consider like a S1 trivial principal bundle over phase space and all the automorphisms of this principal bundle. This happens to be a semi-direct product, which naturally acts in unitary way on classical wave functions this way. So you compose on the right by the diffeomorphism on the phase space, multiply by the square root of the Jacobian, and you multiply on the left, you multiply simply as complex number by this phase, which is a function in this from T star Q to S1. So you can easily check this is a unitary action. And what I want to present is what is the momentum map for this, right? So you remember from my previous slide that what is needed is the infinitesimal generator. So I computed here, right? It has a part due to the action of the diffeomorphism part, which is here given by this vector field X. And there is also a phase part, which is due to the part here, the second part of the semi-direct product. So here, so X nu is a Lie algebra element that acts on this wave, on these classical wave functions. So now I apply the formula for the momentum map that I showed you earlier, which is this one here. And you get this expression here. So all of you recognize here passing from the wave function description to the Madelung formulation description, right? Because you have these 2 terms here written in terms of the phase of the wave functions, which I call sigma and d. So sigma is like a fluid momentum, right? Given by this quantity. D is the amplitude square, right? And in terms of the amplitude and the phase, they take this expression. So you recognize here really the expression of this momentum map. So far for the geometry. Now for the dynamics. So remember that our KVH equation for classical mechanics is Hamiltonian with respect to this Hamiltonian here, where here in the middle you have the pre-quantum operator. And from the previous slide, you remember that we have to check if this Hamiltonian factorizes through this momentum map. So this is the case, right? We can write the KVH Hamiltonian in terms of the momentum map by using this Hamiltonian here, which depends on the momentum and the density in this way. So that's a very natural expressions, right? Because the first term is the momentum multiplying the Hamiltonian vector field, and the second term is the Lagrangian multiplying the density. So almost the simplest Hamiltonian that you could construct from the important object of the KVH equation. So now applying the theorem that I mentioned before, that momentum maps send Hamiltonian systems to Lie-Poisson system, this momentum map sends the KVH wave equation to some hydrodynamic equations on phase space. So the first component is this hydrodynamic equation, fluid momentum equations, and this is the density advection equation. So here it's a Lie derivative terms acting on the momentum. dHd sigma is the velocity of our system. And here you have the contribution of the dependence on H on the density D. So you have this formula. Okay, so as I said, these Hamiltonian helps, these momentum maps helps us understanding the hydrodynamic formulation of this KVH classical equation. Also, I rewrote them in terms of phase and amplitude in order to you to see the difference with the, if you would do the same thing for the KVN, for instance, classical equations. Here you see this additional phase equation here, which has this additional Lagrangian contribution here on the right-hand side. So we keep this in mind, and we will see how this can be generalized or adapted later to the hybrid case. So, but before this, there is another very important unitary action also appearing in the KVH equations that is useful to understand now the link with the Liouville equation. So this has been explained earlier by Cesare and Denis, how we get the Liouville equation. Now I explain this in terms of geometry, namely by applying a momentum map. So since I have this principal bundle here, trivial principal bundle over phase, or the phase space, I can take this classical canonical one form and build a connection on it, right? And I get a pre-quantum bundle. So a natural group to be considered is the subgroup of the previous one, right, that gave the Madelung equations, the subgroup that preserves this connection. So this is also known as the contactomorphism group or strict contact transformations, or just connection preserving, in my case, in our language. And observe that it's no more a semi-direct product. It has a more complicated structure that I will explain later in more detail. So to have a feeling of what this group is, let me write down the Lie algebra, right, which is a simple computation, which consists of all vector field and real functions that are related this way. So the Lie derivative of the canonical one form, this is PDQ only, this A, right, has to coincide with the derivative of the function B. So necessarily from this relation, X has to be a Hamiltonian vector field, and nu has to be the Lagrangian associated to the Hamiltonian given by this Hamiltonian vector field. So we are naturally we naturally have an isomorphism between this Lie algebra and phase space functions. And this isomorphism is simply given by taking the Hamiltonian vector field on the first slot and the Lagrangian on the second slot. So it's really nice because we can understand the Lie algebra of this quantumorphism group as simply the function on phase space with the Poisson bracket. So as I said, this is no more a semi-direct product. It's now a central extension. And here I just wanted to give you the explicit expression of this central extension. But I will not explain this in detail, but just to mention that these connection preserving automorphisms are Lie group isomorphic to the central extension of symplectic diffeomorphism on phase space by S1 relative to some group 2 cocycle. So the study of the quantumorphism group, etc., has been motivated by geometric pre-quantization. This is found in works by Souriau, Constant, etc. And this nice isomorphism is found in a work by Ismagilov, Lozic, and Michor, which I should have mentioned here. Okay, so now let's look at the unitary action of this group. And so I just want to see this group as acting as a subgroup of the previous action that I already mentioned. And so I get this unitary action, same form as before, or here in terms of central extensions. So here I wrote down the infinitesimal generator associated to the action of the quantumorphism group. And now we have what we wanted, right? The infinitesimal generator of this action is nothing else than the covariant Liouvillean that appears in the KVH equations. Of course, this goes back to the Van Hove, right, approach, which considered this action of connection preserving, this unitary action of connection preserving automorphism on classical wave functions. So having understood the KVH equation, because this is the self-adjoint operator of KVH, via all these unitary action and geometry is very useful, you will see also later for the hybrid case. So now what we have more than earlier is the momentum map associated to this. And here we get the expression of the density of the theory. So I just compute the momentum map of this unitary action. I get some formula and I get, so here the amplitude square plus some divergence correction that was mentioned earlier, right? So here it arises as a momentum map. And from this previous general theorem that I mentioned earlier, any solution of the KVH equations necessarily is sent to the Liouville equations via this momentum map, because the Liouville equation is the Lie-Poisson equation on the dual Lie algebra of this connection preserving action, right? So that's where we are with the momentum maps for the KVH equation. So as given here in this diagram. So that's the KVH formalism. Two important group actions, one giving the momentum map associated to Liouville description, one other momentum map associated to the Madelung formulation, and a nice Lie algebra inclusion that relates the two pictures. Okay, so let's now keep all this in mind and move on to the hybrid equation. So the hybrid KVH equation has been described earlier. It's given by this formula, right? As you remember, a first part is the Poisson bracket of the hybrid Hamiltonian with the hybrid wave function. The second part is multiplying the hybrid wave function with the Hamiltonian. Formally, it's just putting a hat, but concretely, it's applying quantization of one particle in a two classical particle systems. Okay, so this is again a Hamiltonian system with the same kind of Hamiltonian as before, and which has nice equivariance property. Okay, so before I start, I would like to present a natural object associated to this hybrid wave equations, which is the hybrid density operator. So the hybrid density operator is defined naturally from this condition. So that's the Hamiltonian function of the hybrid wave equation, given here in terms of the Hamiltonian, the covariant Liouvillean operator. And this d hat is such that we can write H this way, right? The pairing of the hybrid Hamiltonian with this matrix, this hybrid density matrix. A quick computation gives us this expression. So here you recognize the same structure as the classical density earlier in the KVH equation, right? You have some natural expression modified by a divergence term here, which appears in two pieces here. Some contribution of the canonical one form as before, and some contribution of the Poisson bracket of the quantum wave, hybrid wave function and its adjoint here. So remember that earlier, so here, this is just to help you understand this d hat, right? This hybrid density operator. Either you can write it using the kernel notation, right? Or using this compact notation. Here it's just, I'm recalling that it has some nice equivariance property with respect to the Van Hove action discussed before. But we will see much more about this later. So let's now apply our program. We have to find some good unitary actions that help us identify crucial physical quantities. So first of all, there is this automorphism action, right? As before, exactly as before. So the only difference is that now, instead of having diffeomorphism of phase space, we have diffeomorphism of this hybrid space, which is the phase space cross the quantum space, quantum configuration space. As before, I can compute the momentum map, which has the same form as the one for the Madelung equation in classical KVH. Now, concerning the dynamics, we have to check if the Hamiltonian of our theory factorizes through the Hamilton, through the momentum map. So for this, and from now on, we focus on this class of hybrid Hamiltonian, which has kinetic, quantum kinetic energy, classical kinetic energy, and interaction potential. So for this kind of Hamiltonian, it does factorizes through this momentum map, giving this hydrodynamic form of Hamiltonian. You recognize the two terms, right, which are standard from the quantum part. And you recall here the part appearing earlier in the classical KVH equation. Now applying the theorem for equivariant momentum map, I directly obtain that the corresponding momentum and density, hybrid momentum and hybrid density, satisfied hydrodynamic equation, exactly as before. A major insight here is that the derivative, the velocity, right, dh, the momentum, the velocity of the theory the hybrid velocity vector field has two components. The first one is the classical Hamiltonian vector field associated to the classical Hamiltonian part of the, not classical, the part of the hybrid Hamiltonian that does not contain the quantum kinetic energy, right? This HI here. But the second part is the ordinary vector field that you already see in the hydrodynamic formulation of ordinary quantum mechanics, right? So this hybrid velocity vector field has two main components. Both of them play an important role. So again, here I'm just rewriting this in terms of amplitude and phase dynamics for the hybrid wave function. So we recognize here terms, right, which recall you for the phase some part that already appears in the KVH classical description and the new part that also appears in the ordinary quantum Hamilton-Jacobi equation. So here they are mixed in this way. And from a geometric point of view, they take this very elegant form, right? Where here, this is the hybrid vector field that I mentioned earlier in the previous slide associated to the hydrodynamic formulation, right? So that's the dynamics for the phase and the amplitude for the hybrid wave function.
15 minutes left.
Yeah, okay, thanks. So now that we have a hybrid vector field, what about its flow, right? What are the geometric properties of this flow? If we were doing just classical mechanics, the flow would be a symplectic diffeomorphism, right? Giving the classical trajectories of the system. If we were doing quantum mechanics, this would be the Bohmian trajectories. Here we had some hybrid object, which I denote by phi t, and we're using some computations that I don't explain here in details based on these Madelung equations. We can show these two properties of this hybrid flow. First, how the interaction potential breaks the Poincaré integral. Here, that's the integral of P dq, which is broken by the dependence of the interaction potential on the quantum variable, or in terms of transport of the symplectic form. This is the dp dq, dq dp transported by the hybrid flow. So it's not preserved by the hybrid flow because it has this contribution also due to the interaction potential V. Remember, this V is here, right? It's the interaction potential in our hybrid Hamiltonian. Okay. However, now if I consider only the flow associated to the classical part of the system, which is the flow of the first slot here, it does preserve the canonical symplectic form, right? So this first component of the flow gives us an important subgroup to be considered, right? And I will, in the next slides, show what is this group and what is the momentum map associated with this group and what quantity it gives, what interesting quantity it gives. So the group that we consider is this. So these are all smooth maps from the quantum configuration space into this group of connection preserving automorphism of the pre-quantum boundary. So it's easily seen to be a subgroup by some chain of inclusion. It acts unitarily as before by subgroup action. So that's just a kind of Van Hove action parametrized by the quantum coordinates. So I compute the infinitesimal generator, etc. And I get this momentum map this time. This is nothing else than the hybrid density function, right? Or in terms of the kernel notations, just extract this kernel from the hybrid density operator, right? Evaluated, taking the diagonal element of this kernel. So very good. This momentum map has a very important meaning, right? There is, however, a big difference. Now, this time, the Hamiltonian does not factorize through this momentum map. So, conclusion, there is no closed equations for this D, right? You have to first solve for the wave and compute D from it afterward. So this is the summary of this second part on the hybrid wave equations. So this is our hybrid theory on the hybrid Hilbert space. Two group actions, one giving the hydrodynamic formulation that I discussed, another one giving this classical quantum probability density, and there is another map, which is not momentum map, giving the hybrid density operator. All these maps are logically related, but so here the Hamiltonian can be written in terms of d hat. But since this is not a Poisson map, there is no push forward of the dynamic through this map. This is a Poisson map, but this map does not collectivize, so there is no closed equation for D. However, here it does factorize, so we have a closed equation for hydrodynamic version of this hydrodynamic formulation. So yeah, as announced earlier, we were also interested to check whether we have a class of Hamiltonian from which the classical probability density preserves its sign. And without going into the details due to lack of time, I just show you our theorem that we have so far. So if we assume our hybrid Hamiltonian H depends on the classical coordinates and some quantum operator analytically, and these operator commute, right? Assume also that the hybrid density operator is positive at the initial time, then the classical probability density preserves its sign. I mean, this is the classical probability as extracted from the hybrid system, right? However, how we have already seen, the quantum density operator and the quantum probability density are always positive for any hybrid Hamiltonian. Okay, so this closed what I wanted to say about the hybrid wave equation. Now, if time permit, I planned to also very briefly comment on some recent progress we did about using this geometry. So first, to summarize briefly, what we did is to adapt the KVH formulation for other Hamiltonian systems that are not necessarily canonical, like Lie-Poisson systems for classical rotors or more general non-canonical Hamilton equations. So for this talk, I focus on Lie-Poisson systems, right? And how to formulate the KVH equations for them. So this slide is just to tell you that there are corresponding groups acting also in this case. And the key here is to consider G equivariant versions of the group that appears earlier. So this works if the classical phase space is the phase space of a Lie group. So right, if our T star Q is T star G for some Lie group G, and the Hamiltonian, the classical Hamiltonian is G invariant. So if this happens, all what I said on the KVH equation go true if we use this equivariant subgroup of the theory. And the result is this KVH Lie-Poisson equations, right? You recognize here the same Poisson contribution as before. And here you have the Lagrangian, but now on the dual Lie algebra, right? For Lie algebra moment mu. So this is the phase space Lagrangian written on the dual Lie algebra. So for instance, if you have a classical rigid body, this is the kind of KVH equations that you have. And the associated density still satisfies Liouville equation as before given by a momentum map, no problem, right? And now what about the hybrid versions for that? So very briefly, here you may just hear me, listen to me rather than look at the slides because I will be a little bit fast, but just to give you an idea. So the idea is the same as before. We consider a KVH equation for some Lie-Poisson system, like a rigid body, coupled to a classical spin, for instance, Hamiltonian dynamics on a sphere. And we quantize the classical spin using geometric quantization, which is a very well-known process, very well-studied mathematical process to extract some, to associate some quantum dynamics to some given classical system. So in our case, we apply this to the sphere. So we use geometric quantization of the sphere. I don't want to go through the details, just give you the answer that we get. So the answer that we get is this kind of hybrid equations. So given some hybrid Hamiltonian defined on the dual Lie algebra, giving some Hermitian operator on C2, here I took a 1/2 spin with such Hamiltonian function here. So h of mu, which is just a function of the moment 2, plus this part, then the corresponding wave equations that we suggest has this form. So for instance, for the coupled classical and quantum spin, by working on this expression, we get this formula here, where we see, you see here the contribution of H, right, the first plate, and how the Pauli term appears in both terms of the equations. Okay, so let me conclude. So in a first part, I discussed geometric structures underlying the KVH equations for classical mechanics, how these structures help us understand the link with the Liouville equations and the hydrodynamic formations. An attempt to bring this picture to the hybrid level was also made. What works, what doesn't factorize, but still gives meaningful objects has been also discussed. In particular, how the interaction potential breaks the symplecticity of the hybrid flow, for instance. Then I also present a class of systems from which the classical density stays positive, if it is positive at initial time. Then I briefly survey how this setting can be used to produce models for a more general class of classical systems coupled with a quantum spin. Okay, thank you for your attention.
Let's thank the speaker. Yes, we have a time for short questions.
I'd like to ask one question to.
Please go ahead.
I very much enjoyed your talk. It was really a nice talk because I used to work on these topics myself when the Suryo-Konstantian theory was created and all that. And one thing that intrigues me, you nowhere use a Maslov index or a metaplectic correction or something like that. You don't need that.
No, because we only consider the sphere when we apply geometric quantization.
Okay.
if we may want to consider other, then we may need this. Yeah.
Okay.
But most of the constructions are based on geometric pre-quantization, interestingly.
Yes.
So yeah, that's.
I have
Luckily enough, because geometric quantization as such has not proved to be very successful. But pre-quantization, yes, that's nice. Okay, thank you.
I have one, François. This is
Hi.
Igor. So really nice talk. Just one brief comment. Have you thought about the relativistic version? You pointed out covariant a couple of times. And I don't know if you noticed, but I don't know if you saw my talk yesterday. But if you use the proper time formalism that I presented yesterday, the equations that you get, I was working with the square of the wave function in the density on the density part. So you just have to convert for the factor of 1/2. But otherwise, it doesn't matter. I mean, I think this can be very beautifully ported with the relativistic momentum maps.
Yeah, we also think so. Absolutely.
Okay, so maybe we can talk a little more. But the prize is what I didn't get to show is maybe just in a discussion is that you can actually derive Dirac on curved space using that that approach as well. And once you couple the classical relativistic, like Schwarzschild metric, and the Dirac, you get actually a quintessential coupled classical, classical quantum system. And of course, you get to Hawking radiation, and that would be a beautiful problem to try to see whether we collectively can say anything about, right? Because you see what I'm saying.
Yeah. I see.
Yeah. So the formalism that I presented yesterday accepts a metric G. Take that metric to be Schwarzschild, and then you have a Dirac equation in exactly the same formalism, but take it quantized, right? And now couple the classical formalism with the black hole metric and the quantum, and so a beautiful question is, right, whether, for example, the positivity is due to the fact that when we go from classical to quantum, in Madelung, we cancel those terms. In what I derived yesterday, the terms arise due to curvature J, C divided by V, right? So now if that curvature is pretty big, which close to something like a black hole, it will be, they will again disappear, and so you will have a true, a very, very physically relevant thing. And then Wilczek published recently a paper where that kind of a setting can be exhibited in materials. I don't know if you saw that.
No, I didn't see this.
I'll send it to you.
Okay.
Yeah, it's very interesting, and it's basically very similar to the formalism that you presented today. One gets to the scale. They start with Dirac, and then they say, okay, fixed spin, fixed chirality, and you get basically that equation that you showed today.
Right.
And most importantly, this has a potential for experiments, because I think they were going after 2D materials that have some aspects that act like black holes, which is really spectacular. But I'll send
Thank you very much for the suggestion. That's very interesting. That's exactly the suggestion we are waiting for, right? To develop this in this direction. Very interesting. Thank you very much.
At the least, what I can see immediately is that you can use formalism I presented yesterday to develop the momentum map formalism for relativistic case. I mean, that's pretty much direct from what you've said.
Yeah, that's an advantage.
Not easy. Yeah, I don't mean easy. I just mean direct.
No. At least we have a way, a natural way.
Yeah.